Start. So, good morning and welcome to lecture number 12 of mechatronics subject. We are going to see data equation system, and signal processing will be the first part of this chapter. We are going to see analog to digital and digital to analog converters and signal processing. My name is Sachin Thorpe. A signal converter. Depending upon signal conversion, there are two basic types of converter. One is analog to digital converter, that is called as A to D converter. These are classified as flash ADC, RAM ADC, successive ADC. We are having successive ADC, analog to digital converter, in your syllabus. Digital to analog converters, D to A converters, these are classified as weighted register DAC and R to R ladder type DAC. So we are going to see R to R ladder type DAC because it is in your syllabus. There are two basic types of converter, digital to analog and analog to digital. Their purpose is fairly straightforward. In the case of digital to analog, they output an analog voltage that is a proportion of reference voltage. So whatever digital input will be there, we are going to convert it into analog kind of output. In case of ADC, a digital representation of analog voltage that is applied to the ADC input is output. The representation proportional to the reference voltage. So in the case of analog to digital, we are going to convert analog signal into digital form. Now, why it is needed? We'll see why analog signal should be converted into digital signal, because computers only know the language of digital, or we can say binary numbers. So that's why we have this analog signals are continuous, vary with time, but digital signals are having 1 or 0 output. So with the help of digital output, you can control the computers, or you can feed the computers your data. So that is the additional, that is the main advantage of digital conversion. Now, what kind of an analog to digital conversions are there? We'll see. 1-bit analog to digital converter, 0, 1. If there is 2-bit analog to digital conversion, then it is 0, 0, 0, 1, 1, 0, 1, 1. If we add 1 bit extra, that is 3-bit, then what will get? 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0. These type of conversions can happen with the help of that. You can say that if bits are increased, then your efficiency will increase, your accuracy will increase. Now we'll see successive approximation analog to digital converter. So it can consist of op-amp, operational amplifier. The output of SAR is converted to analog out by the digital to analog converter, and this analog output is compared with input analog sample voltage. Okay, with the help of op-amp. Op-amp is nothing but a comparator. This op-amp provides a high or low clock pulse based on difference through the logic circuit. So this is a successive approximation resistor. This is a logic circuit. This is digital to analog converter. Whatever the output will be there, it will convert again in analog form, and it will compare with input voltage Vin. So with the help of that, we can get successive approximation of actual value. So if there are some examples I have taken in last session, so what you'll get to know how we convert the input voltage into digital form or binary form. The SAR is initialized so that MSB is equal to 0. MSB, LSB, I have explained in later section, but you should know MSB is nothing but most significant bit. So it is the first bit. This code is fed into DAC, which then supplies the analog equivalent of this digital code into comparator for comparison with the sampled input. If the analog voltage is exceeding V in, then comparator causes SAR to reset it this bit. Otherwise, the bit is left as 1. So if V in is this analog voltage is of more than V in, then it will become 0. Otherwise, it will be 1. Then next bit is set to 1 and the same test is done, continuing this until every bit in SIR has been tested. And this resulting the code, the resulting code is the digital approximation of sampled input voltage. In your examination, they will ask you to convert some voltages into digital form. So how they are going to convert, we'll see in the example. So this is you can say tree diagram, or we can say logical diagram of SAR, how SAR works, that we are going to see here. So it is clear. Firstly, it will clear all the bits. It will start with MSB. It will set the bit as 1. If DAC output is greater than VS, then clear bit back to 0. Otherwise, all bits check. If the all bits have been checked, then only it will finish. If not there, then it will repeat that particular loop. So this is called as you can say a diagram, logical diagram of this SAR ADC. Now, digital to analog conversion. Data in binary digital form can be converted to corresponding analog form by using R2R ladder binary weighted resistor. So R2R means there will be one resistance of 1 kilo ohm and another 2R, that is 2 kilo ohm. So these are weighted, binary weighted resistors. With the help of that binary weighted resistors, if we use this type of circuit diagram, then you will get the answers in analog format. So R2R weighted resistor ladder network uses two set of resistors, R and 2R. If you want to build a very precise DAC, be precise while choosing the values of resistor that will exactly match R2R ratio. So that is to be remembered. This 741 is this IC is there, and with the help of this circuit, you can convert any signal into analog signal. So conversion of decimal to binary numbers. This is very simple part. Maybe if you have studied in mathematics, the binary number system is base 2 system. Digital system is base 10 system. It is commonly used because computers know only the language of binary systems or bits 0 and 1. Single binary digit are often referred to as bits. In the binary system, number ABC can be written as. So ABC with the help of base 2 can be written as A into 2 raised to 2, B into 2 raised to 1, and C into 2 raised to 0. The leftmost bit is called as MSB. Just now I have told you, most significant bit, while the rightmost will be LSB or least significant bit. These are some digital to analog conversion systems. Properly weighted voltages are summed together to yield the analog voltage output. 3 weighted voltages are summed. The 3-bit binary code is represented by switches. So this is 3-bit binary system. Now here you will see there is 1, 2, and 4. So it means that it is having ratio of 2. So this is called as you can say 3-weighted voltage method. This is again R2R analog digital to analog converter. This is simplified diagram, 4-bit digital converter. If there are 4 bits there, then B0, B1, B2, and B3. This is MSB and this is LSB. So B3, if there are they will ask you to write for 3 bits, then this portion will get cut. For 4-bit or 4 legs digital to analog conversion, this diagram will be applicable. Now, how the digital to analog conversion actually takes place that we are going to see in this next example. If binary input is 1111, voltage V0 is then equal to V out will be equal to Vs and the bracket B3. B3 means bit 3 1 by 2 plus B2 1 by 4, B1 1 by 8 and B0 1 by 16. So your Vs multiplied by this bracket will come into picture. We'll see in examples also. So this example, 8-bit R2R DAC has V reference of 10 volt. The binary input is 100111011. Find the analog output voltage. So with the help of the formula, first bit will be multiplied by 2 raised to 7, second bit will be multiplied by 2 raised to 6, 2 raised to 5, 2 raised to 4, 2 raised to 3, 2 raised to 2, 2 raised to 1 and 2 raised to 0. So when you want to convert digital format, this binary format into digital format, then your answer will be like this. So your answer is 155 here. So this number represent 155 in digital format. We can calculate the analog output voltage with the help of input multiplied by V reference divided by just, if it is 8-bit, you have to divide it by 256. Okay, and this V output will be 6.05 volt. So 256, why 256? Because it is 2 raised to 8. You have to divide it by 2 raised to 8. Alternate solution, how we can solve this example, same example with the help of alternate solution, and the same answer will come into picture. So it is V reference into bracket B7 divided by 1 by 2, B6 divided by 1 by 4, B5 divided by 1 by 8 and B0 divided by 1 by 256. What is this? It is 2 raised to 1. It is 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7, and this is 2 raised to 8. That is 256. And if you will add this, you will get the same answer as previous example. So it is 6.05 and this is exactly 6.0546. So it is accurate answer, but you can prefer this method because this is very easy method to convert the binary number into digital number and then divide it by 256, 2 raised to 8. So that will be easier one. Next example, for a 10-bit analog to digital converter with reference voltage 1 volt, find the digital equivalent of V input 0.6. Now this is also very interesting. For MSB, that is bit number 9, we'll solve this bit by bit. This is 10-bit ADC, so bit number 9 will come into picture. V is equal to V reference divided by 2. So compare V with V in. If V in is greater than V, turn MSB equal to 1. If V in is less than V, then turn MSB off, that is 0. So as we know, V input is 0.6 and V is equal to 0.5. So your MSB will turn 1. Second, compare V in to V, that is V reference divided by 2 plus V reference divided by 4. So 0.5 plus 0.25, 0.75. Again, since 0.6 is less than 0.75, 0.6 is lesser than 0.75, so that bit will be turned 0. 7th bit, V reference divided by 2 plus V reference divided by 8. So it is 625. Again, it is less than 625. 0.6 is less than 0.625, or this input voltage is more than the reference voltage. So again, it will be 0. Similarly, if we'll calculate for 6th bit, 7th bit, 8th bit, 9th bit, you'll see in 6th bit, what happened? V reference divided by 2 plus V reference divided by 16. So it is coming equal to 0.6, which is greater than 0.5625. So MSB is turned 1. And if we'll calculate till the last digit, you will get the answer, or we can calculate the same answer with the help of this particular formula also. And your answer will be, we output is 0.5995, it is equivalent to 0.6, and its digital format, sorry, binary format is 10011001110. So this is a conversion of analog signal to digital signal, or we can say binary signal. Now maybe this example you may find it is a somewhat difficult kind, but if you will practice a lot, you'll get to know these examples are easy to understand. You can solve it easily. You have to check it twice. Also there are some numericals I have you can say written in my blog also. So some numericals are there. With the help of that numericals, you can practice it in chapter number 3. Some numericals are there. I have mentioned that numericals, I have written that handwritten notes are there, so you can refer that numericals for your further study also. So we'll meet again in next lecture. Till then, Sachin Todkar is signing out. Thank you very much.